First problem I want to do here is just one more example of working with these identities and making the correct substitutions, doing the correct algebra to simplify them or get them to a predefined result. Okay, and this one's got a predefined result, and we'll talk about it here in a moment. We're only going to get through example 6 today. Maybe example 7 we'll do next week, but I'd like to move on a little bit just because of time constraints for the rest of the year. This one here, here's my question. Because we have to decide which side to start with. What would be harder or more difficult algebraically to do? Something like, let's say, 2 over 1 minus 3 or 5 plus 6. Which one's easier? Yeah, this one's going to be more difficult, right? This one's easier. This one's more difficult, okay? So what I'm going to do here is we're going to start with the one that's more difficult, okay? We're going to start with the left-hand side. Now, you can start with the right-hand side, but what you're going to find out is that it's going to be very difficult for you to, because we don't have the knowledge of how to do this yet. We haven't seen many examples with this. You get to a point in the right-hand side when you do all the algebra that it provides, it's going to be really difficult to get that after like 2 or 3 steps to look like cosine u minus or over 1 minus sine u. So that one, we're going to start with this as being the more difficult. And that's my suggestion to you. Fractions generally more difficult than things that are not fractions, okay? If at the point you choose the right-hand side and you work through and you do all the correct substitutions, correct algebra, but you can't realize how to get it to match the left-hand side, then basically what you do is say, okay, well, that didn't work for me. I'm going to reattempt this, but choose the other side to start with. Does that make sense? But choosing the most complex, probably 90% of the time, if you're able to make that decision correctly, you will be fine. So I'm going to start with the left-hand side. And we're going to say, obviously, it's cosine u over 1 minus sine u. Okay? Now, this is a new type of strategy that we can add to our toolbox. Okay? Yesterday, we talked about factoring, looking at GCFs, trying to get things to be sine squared, cosine squared, things like that. Now, we get to this, and we do not have any functions that can be rewritten in terms of cosine. Everything is already written in terms of cosine, correct? Or sine. So I can't do that. There's no substitution there. And there are no powers of 2 to make Pythagorean substitutions. Okay? So what we have to do is something creative so that it generates one of those scenarios for us. Do something so that it generates maybe the ability to rewrite something with sine and cosine, or do something that maybe gives the ability to use a Pythagorean identity. Okay? What are you allowed to do to any expression? Let me phrase it this way. What can I multiply any expression by so that it doesn't change the value or what the expression does, but it changes the way it looks? Multiply by 1. Okay? And that's what we're going to do here. We're going to multiply by 1. If I just multiply by 1 over 1, it's not going to change the way it looks, right? Say again. You're on the right track, okay? But if I do that, what happens, because you chose this, so he looked at the denominator and said, I'm going to multiply by the denominator over the denominator. And if you do that, in the bottom, you end up with 1 minus 2 sine u plus sine squared u. And that 2 sine u is going to be really hard to get rid of, okay? So what can we multiply by? You're on the right track, Jim. You're very close. But what can I multiply by so that I don't have a minus 2 sine u? I don't have those middle 2 terms. If I multiply by sine, what I get is sine u minus sine squared u, and then after some work, I'm still going to. Okay, why would I choose 1 plus sine u? What are those? What is 1 minus sine u and 1 plus sine u in relation to one another? Not opposites. Not inverses. Starts with a C. Conjugates. And when I multiply conjugates, don't O and I, by definition, cancel each other out? So now when I multiply this through, on the bottom, I'm going to get 1. So I do first times first, and we do last times last, because we know that O and I are going to be opposite values. And at the top, I'm going to distribute the cosine u cosine u plus then cosine u sine u. Okay? Now, why do we do? One, we don't change the way it looks, but it doesn't change the value. So if I took that red phrase and plugged in u to be 30 degrees, and then took that new blue phrase and plugged in u to be 30 degrees, they're going to equate to be the same thing. Okay? So we didn't change what they do, but we changed the way they look, because we now have generated a sine squared, haven't we? We've generated a Pythagorean identity. If I have sine squared u plus cosine squared u equals 1, can I subtract sine squared u from both sides to get what's in green here? And that would leave me with cosine squared u, right? So that green thing can be replaced with cosine squared u. The top is cosine u plus cosine u sine u. Okay? And this is the reason we did this. At the beginning of the problem, we could not, and at the beginning of the problem, I might have had something like 1 over, or let's say 2 over 1 minus 3. If I had a fraction like that, okay, you can't separate it, okay, because you can't make that like 2 over 1 minus 2 over 3, right? That doesn't work that way, okay, because it's common denominators. But if I had something like this, if I had 1 minus 3 over 2, can I rewrite that as 1/2 minus 3/2? It's kind of it's the inverse of common denominators, right? Okay. Now that I have a singular, so this is my common denominator, I can work backwards and rewrite this now as cosine u over cosine squared u. It's a common procedure once you have a common denominator to actually break them apart. And now I can have plus cosine u sine u over cosine squared u. Okay, now if I look at this here, okay, can cancellation occur? And that's why I like to break them apart. That can cancel, and you're left with 1 over, because there's 2 cosines being multiplied together down here, right? So only one cancels, so I have 1 over cosine u. And then the same thing can happen over here. That cosine u can cancel with one of these, and it leaves me then plus sine u over cosine u. What's 1 over cosine the same as? Secant. What's sine over cosine the same as? Tangent. Is that the same as the right-hand side? Okay. So, a strategy is to, when you have like a 1 minus sine u, 1 plus cosine u, 1 minus cosine u, 1 plus or minus some trigonometric function. It doesn't matter what of the 6 trigonometric function it is. Generally, a good procedure or useful procedure is to multiply by that thing's conjugate. Okay? In the factor of 1. So a convenient, I always refer to it as a convenient form of 1. Convenient because it gets the ball rolling and allowing us to make other substitutions. If you would have started with this side, what happens eventually is that I'm not sure if 100%, but I think you get down to something like that eventually. Okay? No, you don't get to that. You get to, well, let's just do it real quick. I think we might have time. So if I start with secant u plus tangent u, I was just going to do it down here. Secant u is 1 over cosine. That's what most people are going to write it as, right? And then tangent u is sine u cosine u. So ultimately what you're going to do is you're going to be starting at this end and working that way, right? Okay. So I would maybe say, well, that's a common denominator already, correct? So I can rewrite that as 1 plus sine u over cosine u. And at that stage right there, this is where I'm saying you might get stuck if you would have chosen this side, because you don't know, before doing this the first time, what to do next. Okay? But next, what would you do? Because we've already seen this one route. Going this route, we multiplied by that thing's conjugate, right? Well, do I have something else here? Can I multiply by this one's conjugate? Let's see what we get. We get 1 minus sine u over 1 minus sine u. Okay, that's going to end up being 1 plus sine squared u. Sorry, it's 1 minus sine squared u. 1 minus sine squared u. And this thing, I'm just going to leave it as, I'm not going to, a lot of times when we multiply these things down here like this, I'm not going to actually do the distributive, so I'm going to go cosine u, 1 minus sine u. Okay, what's cosine squared the same as? Maybe I should ask it this way. What's 1 minus sine squared the same as? Cosine squared. So can I make that substitution that is cosine squared u? And this is cosine u over 1 minus sine u. And this is the reason why I wouldn't usually multiply these together, even though they are that, that product right there is this, but not distributing that, because now, can you see the cancellation of that one with that one? Leaves you cosine u over 1 minus sine u. And is that what we started with? Cosine u over 1 minus sine u. Okay. So you start that. That's hopefully maybe giving you a visual that when we say we choose a left-hand side or a right-hand side, it never really matters. There will be times, though, when you choose a side that is less complex than the other, that working your way backwards might be harder to do. Okay, so that's just something to keep in mind. So, okay? When you see 1 plus 1 minus a trig function, multiply by the conjugate, and it's going to make things easier for you. On this one, this is an example where you actually, it makes most sense to work on both sides. So you'll work on this side, probably multiplying by 1 minus cosine over 1 minus cosine. And you'll work that as far as you can. Okay? And then you'll come back to this side, and you'll probably multiply that one by secant plus 1 over secant plus 1, right? Make some substitution. You might even be able to make a substitution right away, because that's secant squared minus 1, isn't it? And secant squared minus 1 will factor to secant minus 1, secant plus 1, so there will be some cancellation maybe there that can occur. But you'll work one side, work the other side, and then hopefully as you work through both sides, eventually something on the left-hand side matches to something on the right-hand side, and that is then proof that they are indeed the same expression. Okay, we'll come back maybe if we have time on Monday and actually finalize that one. But what I want to talk about in greater depth today, and this is hopefully giving you an application or a purpose for these identity procedures that we're going through. Okay, because you might say, well, what is the purpose? Well, why do I need to be able to do this substitution stuff? Where am I going to actually use that beyond 7.1? Okay. And my hope is that eventually I can maybe show you some real life applications of the use of these things. But this is, we got to understand this before we can get to maybe those real world applications. These formulas are formulas that are generated by using some geometry concepts, which I'm going to show you. Okay, hopefully we revisit and remember. And then using some of the basic substitutions from our previously known identities. These formulas are very similar to one another. Okay, so we got the formulas for addition and subtraction for sine and cosine, and then also for tangent. But if we look at these four, it is very easy, when they tell me the sign of s plus t, it is very easy to accidentally want this but write one of these other three. Does that make sense? So I'm going to try to give you some phrases that help you, or may help you, that help me remember the order of these components on this side based on what we start with. Okay. Before we do that, though, I would like to actually show you what these formulas are for. Okay. So let's take, I'm going to ask the question, what is sine of 75 degrees? It makes most sense with these problems to do things in degrees. Because if I said, what is the sine of 5 pi over 12, and then ask you, well, what are two angles that add to 5 pi over 12 off the unit circle? Because of common denominators and stuff like that, it's going to be hard to say that that's pi over 4 and pi over 3. Okay? But if it's 75 degrees, can you tell me two angles that add to 75 degrees that come strictly off the unit circle? 30 and 45. Okay? So what we're doing here is we're going to be asked, what is the exact value of sine of 75? Well, the only way we can do that is actually to break it up and say it's the sine of 30 degrees plus 45 degrees. Okay? Now, we can actually, because there's so many, there's like, what, 17 points on the unit circle, 17 different angle measurements that we know. We can take any two of those and merge them through addition or subtraction, and as long as we get 75 when we do that, this will work. Okay? And because of the commutative property, it does not matter the order of the 35 and the 45. Does that make sense? What will matter, though, is the order that we use them on the right-hand side. Okay? So what is being said here is that, get that out of the way. Right now, this 30 is ultimately that S right there. And this T is our 45. Okay? Some textbooks use alpha and beta. Some use A and B. This one, for whatever reason, uses S and T. Pretty sure they're using T because of the distance on the unit circle and the circumference that we've talked about in the past. But now all I have to do is apply this side of the formula. Okay? Now, the way I remember this, if you start with sine, the order of these things go back and forth between sine and cosine. So you're going to say sine, cosine, and now I'm going to say sine again, but it's SIGN in this case. And I say sine SIGN because that sign right there is going to be the same as that sign right there. Okay? So sine, cosine, sine, cosine, sine. Does that make sense? So I'm going to write sine, cosine, sine, cosine, sine. I'll leave my arguments open right now. Okay? Because now I'm going to go back and replace what those angles are, and it goes S, T, S, T. It's always in the order, and all four of these go S, T, S, T, S, T, S, T, S, T, S, T, right? So S was 30, so I go 30, 45, 30, 45. You just want to make sure that you don't go like 30, 45, and then 45, 30. Does that make sense? They have to be in the same order, because on one of those you're taking the sine of 30, and on the other one you'll be taking the sine of 45, and you don't want to accidentally take sine of 30 twice or sine of 45 twice. So now we should be able to evaluate. What is the sine of 30? 1/2. What is the cosine of 45? Radical 2 or 2. Okay. Plus, then, what's the cosine of 30? Okay. What's 1 times radical 2? That's all over 4, right? Plus, then, so that's going to turn into radical 2 plus radical 6 over 4. Okay? That's the sine of 75. Now, I'm going to do the same thing for cosine. Do this a little bit quicker. If I use the cosine one, that's 30 and that's 45. Okay? So it'll be 30, 45, 30, 45. Does that make sense? And the cosine always goes, when I start with cosine, it goes cosine, cosine, cosine. I say cosine 3 times in a row. Cosine, 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 because it's the opposite of what that is. Does that make sense? Okay? Cosine, C-O-S-I-G-N, because plus and minus they are complements essentially of one another, right? Okay, so that's how I remember that one, and then sine, sine. So cosine, 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 sine, sine. Now's my question, what's cosine of 30? Radical 3 or 2. What's the sine or cosine of 45? Radical 2 or 2. I know it's kind of small here to see. What's the sine of 30? 1/2. Sine of 45. Radical 2 or 2, right? So if I multiply that stuff together, I get the cosine to be radical 6 over 4 minus radical 2 over 4. Does that make sense? So that's the cosine of 75. And this one here was the sine of 75. So if I look at my unit circle, okay, and we look at, I'm just going to plot, so right now I've got drawn out an angle of 75 degrees here, okay, which that would be 5 pi over 12 if we're talking about radians. And I'm going to ask it to find the ordered pair. I know it's kind of small, so let me see. Okay, so I'm going to go to the ordered pair. I want the cosine. We said the cosine was 6 minus 2, right? So square root of 6 minus the square root of 2 all over 4. Okay. Make sure I got all this in extra parenthesis here. So I'm trying to write an ordered pair. And then the y value is the square root of 2 plus the square root of 6. That all over 4. If I hit enter, hopefully I got it all typed in right. You see how I highlighted that point right there? Okay. So look at that point. Do it again. Let's see here. There you go. That point right there, okay, is what we typed in. And it's the same thing as M that you're seeing right there. Okay? So we just created the exact values for that ordered pair at 75 degrees. Is that okay with everybody? So if I wanted maybe the exact one at, let's say, 15 degrees, can I take 45 minus 30? And that give me 15 degrees? And then we could use symmetry to find other measurements across the unit circle. Basically what this formula allows us to do, right now in the unit circle, or before today on the unit circle, all we knew was multiples of 30. That was the lowest angle measurement that we could find exact values on the unit circle for. Now our lowest angle measurement is 15. Okay? And once we have that, we could actually go, well, 15 will be all the things that we do with 15. That's as low as we'll be able to go. After Monday, we should be able to go down to 7.5. Okay, but it allows us to find more exact values on the unit circle. Is it okay? All right. Now let's talk about where these come from. Okay. So what I want to do is look at this structure right here. Okay. Don't worry about the algebra. I want to talk about the geometry first. So let me highlight this point, call this point Q sub 1. And this one is Q sub 0. All right. we got a circle here. This is our unit circle. Okay. I'm going to draw out an arc of T. That's the arc that we've been dealing with, right? Around the unit circle. If that's in radians, that distance is the same as the angle, that is the central angle that would subtend that arc, and actually the radius would be going from the origin through Q1. Okay, that angle would be the same as T. Okay. The ordered pair that we've talked about that attaches itself to T all the time here, okay, that X value is the cosine of whatever T was, and it is the Y value is the sine of whatever T was, right? We've been talking about that since middle of chapter 6. Okay? Is everybody okay with that? So that terminal point is identified that way. Now what I'm going to do is once I stopped at T, I'm going to get going again, and I'm going to add another arc of S. Okay? So now if I want to find this terminal point over here where my cursor is, that terminal point is still going to be cosine comma sine of something, but now it's of the arc that has been traced out to get to that terminal point. Well, the arc that has been traced out to get to that terminal point, its distance, it's S plus T, isn't it? Okay, so that point is going to be identified by the cosine of whatever S plus T is, comma, the sine of whatever S plus T is. Okay, we cool with that? Now I'm going to do the same thing, but I'm going to go that direction. Okay, now I'm using the same S, so it's the same length right there as that arc up there. Okay, we'll talk about why that's important here in a moment. But if I go opposite S, okay, that means that this point here is going to be cosine of negative S, comma, sine of negative S. Okay, but I want to show you just why maybe one of our properties is really nice for us. Okay, cosine of negative S. We have an even-odd property. We don't like that negative S. We have an even-odd property that says the cosine of negative S is the same thing as the cosine of S, right? Is that okay with everybody? If we go sine of negative S, we have an even-odd property that says that that is the same thing as the opposite of sine of S. Okay? So writing our ordered pair this way, because the S is now a positive value, is better for us than writing it that way. And you'll see why here in a little bit. Okay? So we're just going to reestablish that ordered pair as those two values. Okay? Now, the part that we might have to jog our memories for is what we know from geometry. Not right now. If we look at this thing right here, okay, does anybody remember what that segment is called, that dotted segment is called for a circle? That is a chord, okay? And that chord subtends or ultimately creates or cuts off or intercepts that arc S plus T. Would you agree with that? Okay. What's that segment called? It's a chord as well, isn't it? And that subtends the arc of T plus negative S, right? Okay. But if we're talking about distances, because these arcs have lengths, okay, does anybody remember what we talked about? Because this black chord is intercepting S plus T, and the blue chord is intercepting S plus T. So these arcs are the same, right, for these respective chords? Does anybody remember what the relationship then is for those two chords? Because they intercept the same arcs? They're the same. Okay? When two chords share congruent or the same arc, then the chords are congruent. Okay? Why is that useful for us? Okay? Well, we have the ability to find that distance right now. Okay? The distance formula in the Cartesian plane is that thing right there. x2 minus x1 squared plus y2 minus y1 squared all underneath the square root. Right here, P1 is an x1, y1, and this P0 is an x2, y2. Does that make sense? If I apply that formula to P1 and P0, we get this thing here in purple. Okay? We actually call this one x2, y2. Cosine of s plus t minus that one squared plus then sine of s plus t minus that 0 squared. Is that okay with everybody? So that's the distance of that dotted chord. Well, should be able to do a similar thing with that then, right? And what we do then with that one is we get q1 to q0, that distance, we go cosine of t minus cosine of s. Cosine of t minus cosine of s, those are the difference in your x's, and we square it. And we take sine t minus negative sine s. Minus negative sine s, and then we square that. Okay? And that gives me that distance. So what do you know geometrically about these two distances? They've got to be the same, because their arcs were the same. Okay? So if those are the same, then we could basically write an equation that looks like that, right? We could take the purple one equals the black one. And because they're both radicals, it's a one-to-one relationship. The only way that these two radicals are going to be the same is if the radicands are the same, right? So there's my two radicands. Okay, it's taking this purple radican, and that's this top line, and this bottom radican, which is this bottom line. And set them equal to each other. Okay? Now what we've got here, and this is where algebra comes in handy, that is a minus b squared. So you're going to take that and square it. Then you'll take these two, multiply together, and double it, right? And then you'll square the last term. This here, you could do the same thing, but minus 0 just makes this sine of s plus t squared. Down here, you have another binomial squared. So square this, multiply these together, double them, and then square the last term. And the same thing here. And when that happens, you get this. Okay? And now we're going to use that. I've already got it cut out over here somewhere. What in the world? Okay, so this was when we took that. I've already squared things and done all the necessary combining of like terms when we squared all those things underneath those radicals. Okay, and now I'm going to look at this left-hand side. What does that right there turn into? Okay, so cosine squared s plus t plus sine squared of s plus t. And s plus t is just some value, right? So maybe it's 75. So if I had cosine of 70, so cosine squared is 75 plus sine squared is 75, what would that ultimately be? Amari? It's going to be 1, right? Does that make sense to everybody? That goes to 1. And then I'm left with negative 2 cosine of s plus t plus that one plus the one that came from that identity, so I get a total of 2, right? Okay. Let's look at the right-hand side. Looking at the right-hand side, what does cosine t plus cosine squared t plus sine squared t turn into? That's a 1, right? What's cosine squared s plus sine squared s turn into? That's a 1. Okay, so together you now have 2 minus then 2 cosine t cosine S plus then 2 sine T sine S, right? Okay. Look at that equation. What's going to happen with this 2 here and that 2 there? Cancel out. What can I divide everything by? -2. Divide by -2. Those go away. Divide by -2 here, and this turns into a minus, right? Is that our formula? Yep. Okay. Now, we a lot of times, because the commutative property, I can rewrite this as cosine of S plus T, flip-flop these two, so it becomes cosine of S cosine of T minus sine of S sine of T. But let's say that we wanted cosine of S minus T instead. Is cosine of S minus T the same thing as cosine of S plus negative T? Does it still say minus T? So let's go ahead and apply this property, this rule here, to this stuff. So I got cosine of S. Now it'd be cosine of negative T minus then sine of S sine of negative T. Is that okay, everybody? What's the cosine of a negative T? It's cosine of T. So this thing just turns into cosine S cosine T. And now what is the sine of negative T? Negative sine of T. So this thing here brings in a negative, and I can bring it out in front here with this negative, so it turns into a plus. Sine S, and that thing then turns into sine of T. Is that so that is the cosine of S minus T. That's the difference formula for cosine, right? Now we're running out of time here, so I'm not going to show this right now, maybe later next week. We only have the cosine sum and difference, right? If I want the sine sum and difference, we're going to use the relationship that sine of theta is equal to the cosine of pi over 2 minus theta. Is that okay with everybody? We'll use that. We'll make a substitution in here. Using that, we'll evaluate this. So that will leave us eventually with like cosine of pi over 2 somewhere. It'll leave us with sine of pi over 2. We'll evaluate those. And what spits back to us then, and like I said, with the time that we have right now, what time we get out of here? 40. Well, let's go ahead and we might be able to do this in the time that we have. Trying to think. If we so we know that like sine of x or sine of theta is equal to cosine of pi over 2 minus theta, right? Okay. I'm going to write this. I'm going to say sine of S plus T is equal to, now just bear with me here, okay? So now this theta is going to be S plus T. Is that okay with everybody? So now I'm going to write this as cosine of pi over 2 minus this quantity S plus T. Okay? Now I'm going to distribute that minus, and it's going to give me cosine of pi over 2 minus S minus T. Is that okay? And now what I'm going to do is I'm going to say, well, that's cosine. I'm going to use my associative property. I'm going to group pi over 2 minus S first, and then minus T. Now I'm going to run that through my cosine difference formula, which my cosine difference formula goes cosine, let's see here, it goes cosine of something, cosine of something, cosine, so plus, and then sine of something, run out of room here, sine of something. So hopefully we can maybe fit all this stuff in here. And those somethings go pi over 2 minus s, okay, and this is going to then be t, and this will be pi over 2 minus s, and then this will be t, okay. Now, just to make things easier on ourselves, okay, because we could use the difference formula again, but don't we know that cosine of, let's just say, s is equal to the sine, let's do it this way, right, because this will be more direct. The sine of s is equal to the cosine of 90 minus s, or the pi over 2 minus s. Does that make sense? Is that thing right there? Can I replace that with sine of s? And I have cosine of t plus then. So now I need this thing here to be replaced. So we know that the cosine of s is equal to the sine of pi over 2 minus s. Those are the horizontal shift, the transformation rules that we talked about. So that is going to be that there. So I can rewrite this as cosine s sine of t. And now, okay, what we have here is the sine, this is what we started with, for the sine of s plus t equaling sine of s cosine of t plus cosine of s sine of t. And that's our sum rule for sine. Now, if I wanted the difference rule for sine, I do this. Substitute that negative t in for cosine of t in that first product, and sine of negative t in that second product. Use my even odd properties, and out spits sine of s cosine of t minus cosine of s sine of t. And that's how those are generated. Okay. Now, I'm never going to ask you to replicate that. I'm never going to ask you to do that with those values. We'll do specific values on Monday. But what I think is important for you to realize, and what makes these things, I think, easier to understand, is to know that they have a backing, an algebraic, a geometric backing. There's logic behind them. Does that make sense? Okay. I think it gives a better idea of what we're really trying to do with these and why we have them. Okay. I don't want to say all of them, but most of our other formulas, especially the ones that we see early next week, double angle and half angle formulas, stem from these four. Okay. And I say these four, I already talked about the tangent one, but if I know what the sine looks like of s plus t, I know what the cosine of s plus t looks like, how do I find the tangent? Divide the sine by the cosine. And I'll go through my evaluation, I'll do some identity work, and out spits the tangent function for those sums. Okay, so that's something we'll work with next week. See you.